Hello everyone, my name is Sungmin. We are expected to begin our capstone project presentation today. Our capstone project presentation topic is the virtue cycle, an adaptive human-in-the-loop pipeline for rapid development of high-fidelity diabetic retinopathy segmentation models. This is the full poster for our study. I will walk you through each section of the poster in order. In the introduction chapter, diabetic retinopathy is one of the leading causes of blindness worldwide, affecting approximately 130 million people according to the WHO. In Korea as well, DR is a major cause of adult blindness, highlighting the critical importance of early detection and accurate diagnosis. However, obtaining high-quality pixel level labels for training precise lesion detection or segmentation models remains a major challenge due to the expertise, time, and cost required for medical annotation. To address this issue, our study proposes a low-cost, high-efficiency human-in-the-loop pipeline that improves model performance while reducing annotation cost even under limited labeling resources. Next is the related work chapter. First, active learning. Recent studies have demonstrated that active learning effectively reduces labeling cost and improves annotation efficiency. When uncertainty calibration is combined with data diversity, labeling workload can be reduced by up to 50% while maintaining comparable model performance. Second, HITL strategies have also been shown to significantly enhance model accuracy and stability. Additionally, uncertainty quantification not only helps detection segmentation errors, but also increases clinicians' trust in AI systems. This figure illustrates the overall architecture. The process begins with the unlabeled pool, which contains all unannotated images. Second, the initial model performs inference on this unlabeled data, and images are selected for labeling based on our sampling strategy. The selected images are then sent to ophthalmologists who annotate them using our annotation platform. That annotated images are fed back into the training pipeline to update the model. The updated model is also integrated into the annotation platform to provide initial predictions, which reduces annotation time for clinicians. Ultimately, the improved model aims to be used in real-world clinical workflows. Next is the materials and method chapter. We use two datasets. The first one is NMC dataset, provided with approval from the National Medical Center in Korea. In this study, it was used to measure annotation time. The second one is TJDR dataset, a publicly available high-resolution retinal fundus dataset collected by Tongji University in China. This was used for initial model training. We focused on detecting three types of DR lesions: microaneurysms, hemorrhages, exudate. For object detection, we used YOLO version 8X, the most complex model in the YOLO family, selected for its ability to detect small pixel-level lesions, such as those seen in DR. We evaluated four sampling stretches across both experiments and the deployed service. The first one is average confidence. After running inference, we prioritize images that show lower mean class confidence, since these are more likely to need human review. Second one is random sampling. In these stretches, uh, images are selected purely at random. And third one is hybrid sampling. This method combines both approaches. 70% of the images are chosen based on average confidence, and the remaining 30% are randomly sampled. The last one is Monte Carlo dropout. Each image is inferred 10 times, and we select those with high variance in predicted confidence, as this indicates model uncertainty.
We've developed a unified annotation platform that allows clinicians to combine, compare, edit, and finalize both manual labels and AI-generated labels within a single interface. The platform features a keyboard shortcut-driven workflow, and it has been continuously refined based on medical UX feedback. It is currently being used by ophthalmologists at the National Medical Center. And next is experiment and result section. The table and graph above show the number of images used in each active learning round and the accuracy convergence of each sampling strategy when the initial model was trained using the TJDR dataset. Although the deployed clinical service uses a model trained on the NM's dataset, this experiment was conducted to compare the convergence speed of the various sampling strategies. As shown in the table, 81 images were used in the first round, and followed by 50 sample images per round in subsequent iterations. And the bottom of graph visualize the convergence trend for each strategy, and the metric MAP represent mean average precision, and MAP 50 indicate average precision at an IOU threshold of 0.5, and IOU means intersection of union. And in terms of MAP 50, random sampling initially boosted performance quickly due to its diversity. In the later rounds, however, hybrid and Monte Carlo dropout strategies converged to higher final accuracy. And from the precision and recall analysis, hybrid and Monte Carlo strategies achieve the highest precision by reducing false positive, and recall showed a similar improvement pattern. And in our real service pipeline, we dynamically adjust the strategy. And all the stages we use random sampling, and middle stages we use Monte Carlo dropout, and finally later stages we use resource efficient hybrid strategy. And this slide shows an actual retinal fundus image annotated by a ophthalmologist at the National Medical Center using our annotation tool. And the table and graph on this slide show the average annotation time per lesion based on 6 retinal images. In the non-AI condition, each annotation required 13.64 seconds, and in the AI assistant condition, this time decreased 6.68 seconds, representing a 51.03% reduction. Overall, we confirm that the value of AI assistance becomes even greater as lesion complexity increases. And finally, conclusion. And this work present an adaptive data construction pipeline using human-in-the-loop interaction between AI and medical professional to overcome the high cost of medical image labeling. By integrating AI generated bounding box proposal with expert verification. The pipeline efficiently produced high quality annotated dataset from downstream research while supporting model development. And it reduced average per box labeling time and showing that both high quality dataset and high performance diagnostic models can be generated with limited resources without large scale manual annotation. And for limitation, the amount of labeled data is limited and requiring collaboration with medical experts to acquire additional data. And sampling strategies and human-in-the-loop cycles in active learning pipelines require systematic improvements with auto-tuning to dynamically adjust. And finally, future work. We plan to generalize the proposed efficient data construction process to other high-cost medical imaging domains such as CT and MRI to validate its scalability and applicability. Uh, Thank you for listening.